You can also do like.
Yes. Okay, everyone. Last session of the day. So the idea here is just to provide like a forum for people who did not have a chance to present and show their work, uh, discuss anything. So today we have James Berragan talking about Kafka integration for Cassandra CDC. Then we have Jordan West talking about improving disk access patterns during compaction and streaming. And finally, we have Bernardo Botella going for CP42 constraints framework. Give it to James now. And 10 minutes each, and then 5 minutes per.
Okay. So hi everyone, I'm James. I think I know most people in the room, but with Cassandra coming up to 12 years, I think. I first joined Kuno, which was a startup for quite a long time now. So what I've been working on recently is a CDC solution that we are building into the this is to enable real-time analytics, responding to changes in the database in real time, and I'll just walk through the CDP that I prepared. But I was going to take a risk. First of all, it's been a risky endeavor this week, but I think I can do it. So on the left, I have CCM running 3 nodes, Cassandra cluster locally, and I have running against those 3 nodes the Cassandra Sidecar with CDC enabled. So I will go ahead and create an example table here. So here we have dummy music library. This flag here, CDC equals to true. So yeah, we'll just and I'll go ahead and just insert a value into my table there. And here we have a CDC mutation coming out. This is average requested by those teams, but trying to keep the data format pluggable. Seems to fit the bill. So here we have sort of outer envelope with metadata about the mutation to insert, which fields are updated, table key space, and yeah, schema UID, which I'll talk about later. And then within that, we have this payload, which is the actual mutation. So the Beatles Let It Be to my album, and then it's got various more complicated collection types. Just demonstrate that. So I can do some other things. I can do an update, so add some tags to my songs. Add some updates. Payload with the individual exact change that occurred in the database. Do deletes, so I'll do a partition delete. Provides the primary, what's the primary key? Yeah, primary keys and the operation type. I can do a range tombstone, serialize that here with this range predicates, and then I can also do a TTL just completeness, so returns with the TTL attached notation. Sorry, is that better?
Stop from the beginning.
So what's going on next? So we have this flag CDC equals true, which I think Josh would be able to tell you more about. So
I don't know what you're talking about. I'm completely uninvolved. Yeah, you've already got to my first question.
So this is a feature in Cassandra. It will essentially hard link the commit log segments to a separate directory, CDC raw. And it's from there that the sidecar can read the mutations. But obviously with Cassandra, for consistency, we need to read across multiple replicas. So we have equivalent APIs in the other sidecars. So we call those APIs to pull the commit log segments from the neighboring replicas. We attempt all of them, but obviously we can handle one node being down. From there, we then stitch the read in the commit logs, deserialize the mutations, match them against the replica copies, and then pass it over, convert it into Avro, and then publish it to Kafka. Back over here. So yeah, I sent this CEP out to the community a couple of weeks ago, I think. If you have any comments, please chime in on that thread. Discussions. So yeah, the approach I mentioned is essentially read the commit log segments from all the replicas, deserialize them. We have these sort of classes for representing Cassandra data types and features, and then a pluggable interface for deserializing and converting into another data format. We found that CDC requires some amount of state to operate. So the most obvious part is you need to store the marker for where you last read to in the commit logs. So that's one part of the state. It's pretty small. It's about 64 bits, or 64 plus 32 bits. Then you store that per Cassandra instance. And then, given that we're reading to achieve consistency from multiple replicas, there can be scenarios where we receive or read insufficient replica copies. So for that purpose, what we do is we hash the mutation and we store the number of copies that we've received from that mutation. And then in subsequent epochs, subsequent batches, CDC, we compare the mutations with what we have in memory to see if we've already read this mutation. That's how we can achieve the consistency level. And this state is pretty small. The markers are going to go above a few bytes for a cluster. This can get a bit larger, but we're still talking kilobytes. And for this, we added a special table in Cassandra to store this. So the table here, CDC state. So it just has a job ID, which is just a sort of string to namespace the job that can be reset. And then we have this sort of sharded token range in order to store the state blob. So this is just compressed CDC state blob that we persist every epoch, every epoch of the CDC stream. And we only read from it when we need to recover. So if the sidecar's bounced or if it crashed, then we'll recover from there. Yeah, another part we added to the sidecar is just some configuration. So this is mostly for storing like Kafka configuration. There's some CDC options, like how frequently you want to run every epoch. It could be like set upper limit over a second or 10 seconds or whatever you need. But we've also are looking to improve this and move this into a sort of CQL syntax. Bernardo will probably can tell you more about the ideas there, but essentially you can configure a data sync, something else, and provide all the configuration options in there, and data source equivalent. Another aspect we found useful is integrating with an external schema store. So Cassandra teams are going to be changing their schemas all the time, adding tables, adding columns, dropping columns. So that sort of continuous schema evolution needs to be handled as part of the average schema as well. So what we do is we take the Cassandra schema, we generate an average schema from that dynamically. We publish that out to a schema store. There's a few different implementations out there. But yeah, again, we've tried to keep it pluggable. And so that means that any schema change made in the database can be published to the schema store with a unique identifier. Then any mutation sent downstream can have that schema ID sent in the message headers. So then any consumer can look up the correct schema from the schema store and towards any breaking changes. I'll quickly finish up because I think that's 10 minutes, but there's some other issues, but mostly related to the transport layer about large blob support. Kafka has limits of a megabyte or so, but we're going to work with the Kafka community to try and improve that, possibly offloading large blobs to S3 or some other blobs. Yeah, that's the CP really. Any questions?
I think I just missed it. So the consistency level thing is like if I write a local form, you make sure that like a local form actually occurs on the stream before it is into Kafka.
Okay. So we'll read at least 2 copies.
Does it dedupe them then? Okay. And even if, so if I write it 1, does it dedupe the other 2?
Write it 1.
Yeah. So like I write it 1, so I only block for 1.
Right, block for 1, but then what? We have a consistency level in the CDC's configuration as well. So
so not the consistency level from the request. It's the consistency level from, okay.
So we'll configure that on the CDC side.
Interesting, okay. That's an interesting interface. It's like I wonder about tables where like the consistency level that's used is mixed.
Yes.
Does it only work with the locals or does it work with like each one?
For now, we're doing DC local.
Okay.
We haven't looked at the possibility of cross DC, but it should be fairly straightforward to add that.
Okay. So it doesn't matter what you write with, it matters what you configure CDC's consistency level.
Yeah, I mean, we could expand that configuration to be per table as well, but
yeah, that I would definitely do.
Yeah.
Jordan, why would you write a CL1?
Yeah.
There are a whole host of people who write at CL1. For example, our entire tracing infrastructure writes at 1 because why would you pay the cost for something that you read maybe 5 of the 20 million traces that you store? So our abstractions have something called eventual mode, which is 1. 15 to 20% of people use that. They also reduce their application factor.
What is the use case for I guess what I'm trying to understand is why would you want, if a mutation lands on the node, why would you want to apply local quorum and effectively miss the mutation as part of the CDC? Because it's not like it's going to disappear from Cassandra, it will be prepared and out. So it's written.
So you're saying rely on.
So in theory, the idea is like you're saying, as a downstream CDC consumer, when things hit a quorum of nodes, because it's the assumption of, okay, people are reading nodes, that data is not going to be visible to them. So let's have what's in CDC match what's visible in Cassandra, but that's predicated on.
It might be visible.
Right, correct. So that's predicated on, and this is the problem that I ran into with CDC and punted on, which is getting the CL and the visibility in Cassandra to match the CL and the visibility in CDC is effectively impossible. You're going to have to make a choice and draw a line in the sand and say, this is how this is going to be configured. But I could see an argument for like on a table basis saying, like, when data hits this many of the nodes for this given table, let me know downstream. But past that point, like, what are you going to have like per mutation, like per mutation respect inside CDC, and then when the CDC visibility matches the mutation. Like
I guess I kind of look at it and I'm trying to figure out when I would use that and when it would be like a landmine, because if the data is written to one node and then read back later, it's going to get repaired or repair process. I'm just trying to think of when someone wouldn't want that. When the mutation does land on them. And part of it is really just, I think people shoot themselves. But
Yeah,
that's all
well,
I do.
so this is part of the common advantage with CDC originally. Like, so the mutation lands on one node, you feed it downstream via CDC, that node dies before anti-entropy. Now you have data downstream that doesn't exist in your database anymore. So what do you do?
But you do, you have the Kafka string.
What?
This stuff is really hard. So do the sidecars now communicate to do this deduping? Like where does
They
the,
don't communicate.
sorry,
They don't communicate.
okay,
They so they simply read the bytes from the other. So there's a sort of commit log API that's very similar to the block read API.
Oh, okay.
Exposes the bytes, pulls it out.
okay, so it's talking to the other, like, so now the sidecar is talking to multiple Cassandra.
Not the Cassandra, but
Sounds like.
Well, it's pulling data from
the other side.
nodes.
it's pulling data from you, just but reading it directly. But the
But like, where does the request go to? Like, how do you network to that?
This other side.
through the other side.
Okay, so the sidecars are communicating.
Yes.
Yeah,
So each side.
but not coordinated.
Fair.
So each Cassandra node has sidecar.
Yes.
Right. So what happens in a replica set is that the first sidecar, that replica set, is talking to the remaining two.
Okay,
Right?
yeah, that was what my question was, is that happening? Because in my mind, I had a model that the sidecar was this thing that only talked to its local node.
It didn't talk to its own node, but it did not do for the CDC. It goes out to the other side.
Right, so that's what I'm saying, it's changing the sidecar model.
It's stealing the dollars
Yeah.
from its peers, ensuring that consistency level is met, that you've configured, and then you can do CL1 if you want, right?
No, my question is more about like again, when I go to deploy the sidecar, my mental model was the only thing I need to care about is the sidecar talks to the local node. If I turn this on, I now need to care that my sidecar is not talking to other sidecars.
And the alternative would be no duplication, and every sidecar vomits every single thing it sees
Yeah.
to the consumer, and then you
I've
just,
seen
like,
this
start
architecture.
documenting stuff.
And I figured.
Yeah. So it's like, you're gonna have to pay the piper at some point.
Yeah.
That was pretty
Okay, we
acceptable
need
to-
to move to the next topic, guys.
James, this is awesome. It's probably the most.
We can continue the discussion.
Was it really not?
So by the way, I found out that like yesterday when we tried to demo Xbox, they were actually having an outage.
Oh.
I got that email.
Say cook, please. I've tested it and you've already scanned things.
Am I just going, Apollo?
Yes.
Go for it.
Yes. Relax. That just makes me around my dogs. So anyways, I'm gonna talk a little bit about the patch that John and I have been talking about a bunch this week. It's Cassandra 15452. I'll start before I dive into the implementation, just a quick status. We have this patch on 4.1. I'm getting ready to deploy that internally at Netflix. And then we have this patch on 5.0. Caleb was kind enough to start reviewing it. We were downstairs before this going through it. So I think minus like nits, the general structure looks good to folks who've looked at it. And then David is kind enough back there to be writing a test in quick theories because my testing was more in our infrastructure. So I think everyone in this room knows this. This was a talk I gave to my team, so a little bit. But asset tables aren't one file, right? There are multiple files. The ones we care about for this talk are the data file and the compression file. We also have 3 different ways that we can access our data files in Cassandra. We have this essence mode mmap, which mmaps both the index file and the data file. We have mmap index only. Hint, it's red because that's the one you should be using most of the time. That's what we use at Netflix. We saw horrible performance issues with mmap and mmap. So the index file is still mmap, but the data file uses regular file IO. And then there's standard, which uses regular file IO for everything, and you shouldn't use that either. So in an SS table, logically, we have all these uncompressed chunks. I'm only gonna be talking about with compression today. That's all this patch touches, and also like, hopefully you're using compression. So we start with all these uncompressed chunks. They're always chunk size in kilobytes. So when you set up your compression, every compressor has the setting. You pick it. I think the default's 16 these days. It used to be 64. 64 is way too big. You'll see why in a moment. All of those chunks then get put through the compression algorithm, and they end up being less than or equal to chunk size in KB, right? So if you had like 1-to-1, no compression, you'd get something that's equal in size. Otherwise, you're going to get something smaller. So it's always less than, let's say you set it to 16, it's always going to be less than 16K. This is important for the read path, which we'll talk about in a moment, because you don't want to decompress stuff that you're not going to read. So this is what the read path looks like. We figure out what compressed chunk you're in. So we look at that compression info. We look at what position in the file. We figure out what compressed chunk that's in. And then we uncompress it. And then we grab the partition out of it. And so that's how the single partition read path works. If you need to read the partition that's next to it, you're going to do the same thing. If you need to read the partition that's next to that, you're going to do the same thing. And guess what? That's what compaction does. So this is what compaction really does. If you have a data file with all these different chunks, they're all less than chunk size in kilobytes. We read each chunk individually every single time in compaction as we're ripping through the file. And so that's why you see what you see in John's output are these like 65K and then 512, and then sort of bouncing between a minimum and the maximum chunk size, basically. Really, really bad for EBS, not great for NVMe. You're just basically throwing away IOPS. Each one of those can convert into IOPS. There's some page cache stuff which we can talk about in a moment, but we'll see sort of like how performance is impacted here. So all the patch does is it reads the red area all at once. So it reads all those chunks together. And so that way, instead of doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 IOPS, you do 1. On EBS, especially, this is really important, as John talked about in his talk. That is the like we set it in our test, the 256K. That is the largest IOP you can do in EBS. And then John, I think remind me, like if you do something smaller than 64K, you're gonna do a 64K read. 16. So when you see those like 4K reads, you're actually still going to get 16 from EBS, but then you're gonna go back and get the other 4 later. Again, caveats and page cache stuff. So that's all the patch does. And so you might ask, like, well, why don't we just turn on read ahead on like the Linux node? And that's because we've had a lot of benchmarking done by folks like John and others, which show that your reads get terribly slow when you turn on read ahead at the file system level. And that's because now you're starting to read bigger than this chunk just to get that little bit. So everything else that you read is going to get thrown away. So money where our mouth is. We used IOStat for these graphs, and I'll show the axon-ops graphs again as well. The blue line is read IOPS. The orange line is write IOPS, and that's just basically like compaction, like dumping the file because we close and then we fsync all at once. So you kind of ignore the orange line for this and just look at the blue lines. We just couldn't pull them out of the graphs easy. And so you can see our IOPS are hovering around 3,000. That is the default limit in EBS. So you have to pay extra to go above that. This is your throughput in that, and it's about 20 megabytes a second. So
I think it was 12.
yeah, so it's really low. So when you sit there and you like up your compaction throughput and you're on something like EBS, you're not actually doing anything. So I have teams that come to me all the time like, hey, can we make compaction go faster? Let's bump up the throughput. You can raise the number, it just doesn't do anything. So this is after. You can see the IOPS went, there's not even 3,000 on the left anymore. So that was before, after. You can see our IOPS are much smoother and more predictable as well because we're just churning through 1 256 chunk of the file at a time. And then you can also look at our throughput here, matches that well. This is up at I think about 80-ish, and then you'll see in our next test where we got it up to about 200 on some beefier nodes. So this is from a test where John and I basically, the dip is where we shut off the node, reconfigured it, but you can see on the left, the green line is basically where the other 2 lines were. So we're looking at 30 megabytes a second for compaction off of EBS normally. And then once we turn on the patch, you're looking at over 230 megabytes per second. We had unthrottled compaction entirely, so you can see here, doesn't matter what your compaction throttle is on EBS unless you're going to set it like down to 8 megabytes a second. So here now, like the throttle actually matters, right? Like I can set it to 128 megabytes a second and like hit it. So yeah, anyways, that's the patch, that's how it works. I sort of tackled this at the beginning, but I'm hoping to get this into 4.1 because I think it's in my mind, it's a bug. Yes, it's a long-standing bug. If the community pushes back on that, I will just backport it internally. I have the patch and I will deploy it and reap the benefits and make it available for the folks who also run 4.1. But it will go into either the 5.0 branch or trunk. That's what we're currently reviewing. A couple other caveats. It doesn't support BTI currently. I'll do that next. The reason it doesn't is the way BTI uses the subsystem where the change had to be made is very different. It reinstantiates kind of like every time it goes to read, whereas the old path just instantiates once, and so it makes it a little bit more difficult. John?
I think that, correct me if I'm wrong here, but I think that you said that it creates a new file object.
Yeah.
On the off chance you can, please use fadvise don't need, and we can reduce page cache churn on that.
Yeah, so that's also part of the next steps. Fadvise don't need. I think we actually talked about why fadvise don't need doesn't work, because I think we talked about this before, but we talked about direct IO instead.
I just want to make sure I understand why, from a read ahead, that compaction read ahead in space good. Just because you don't want it on reads, but you do want it on compaction?
Yes, exactly. Yeah, it makes reads slower. So like if you go look at John's been saying for years, set your kernel read ahead to like 4K. And before we did this, I went and benchmarked that myself. I also reproduced like all of John's results just to convince myself like let's do it. And turns out he was right. So yeah. And
does the cache you configure, is that per compaction task? So you have to scale it for your concurrent vectors?
No. So it's actually a little bit worse. So Cassandra internals deep dive, everything in the read path is single threaded until you get to the compression decompression code, and then it is shared across all the threads. So the way that it works pre the patch, like here, is there's a thread local byte buffer, and so each thread gets that thread local byte buffer, and it just uses it and it never reallocates it. So what we do is we make a thread local read ahead buffer, so the red one, but we have to scope it per file because the way reads work, that buffer, like you can read this chunk out of that buffer, and then another file is going to be read and it's going to read this chunk, and so you have this, if you just had a thread local, you'd be reading out of another file. So that's like the nasty part of the patch, and but there's no getting around it.
Is there a way to cap the total, the sum of all those read and cache sizes?
It's capped on basically the thread concurrency and number of files, but and then there's like when I was talking with Caleb about review, I don't know why I keep wanting to say Blake instead of Caleb. When I talked about with Caleb, I was like, please review where we throw away the buffer and close, because this is the potential for a memory leak is right here.
And when we have a really busy L0, does it become unhappy?
That is part of like what I want to push and test more. But my inclination is no, because even today, right, you're just doing this. So when you have a really busy L0, what we've seen when compaction gets behind on EBS is you blow through that IOPS limit and end up hitting the most IOPS you can get on GP3 is 16,000. And like I was looking at a cluster today that hit that during compaction. And for folks who don't know, when you hit the IOPS limit in EBS, your performance goes through the floor. Like a lot of people, we run a large portion of our fleet on EBS. I have a cluster, 384 nodes doing over 2 million operations a second, backed by EBS with over 2 petabytes of data in 4 regions. It works. It just doesn't work once you reach that IOPS limit. Sweet.
Right. With this, you can hit the throughput limit.
Yeah. So in GP3, you hit both. Or you can configure both, and yeah, so technically what we were hitting there was the throughput limit. And then we went to raise it. EBS GP3 has this stupid limitation that you can only change the IOPS and throughput every 6 hours. And so we had just changed the IOPS, and so it didn't let us change the throughput in the test. And so we were like, well, we could hit the limit.
And this is on non-provisioned IOPS, right? Or is
this is GP3. So not the IO2 Block Express and stuff like that.
Do you expect similar gains for local SSDs as well?
So on local SSDs, we do see IOPS reduced significantly. You don't see this order of magnitude difference, mainly because you can get higher throughput on SSDs. You know, like I would argue that like having less IOPS then put in your queue will always help your disk queues. So it's not as pronounced, but it is beneficial, is what I'd say. And then also you're doing like less copying, and like John talks about, like you're going to be doing less context switching from user space to kernel space and back and forth. And my counter to him is usually Cassandra's so slow in other ways that you don't see the effect of that, but like as we speed Cassandra up, we're going to see that more. So the more that we can smartly use the kernel APIs, I think the better.
Slightly related topic, but one thing we found with the analytics library is the reading the compression offsets, particularly for large SS tables, causes really horrible heap fragmentation. Is that something that's already managed in example? Is that something
I would have to look more, a little bit separate than this. The other place I should mention is we talk about this mostly in the context of compaction. This code actually works also for range reads. So if you're doing a multi-partition read, you're also more likely, right, to be reading these next to each other. So you want to grab that whole chunk ahead of time. And then the other one is in repair when you're building the Merkle trees. You're also currently doing this, and so switch it to this.
So the really interesting thing there is going to be, for me at least, to look at the performance of the DataStax Spark connector, because I haven't verified this, but my gut tells me that one of the major limiting factors there with performance is the fact that it's going to do a ridiculous amount of I/O through very, very tiny reads. And this patch should reduce the number of syscalls by an order of magnitude. It should. I think it will probably result in a pretty significant boost in performance for everybody that's using that.
Similarly for us, we have a use case, my least favorite use case, that consistently does what we call all world reads. So we have this like recipe where you can, do a scan over the entire ring. And when they were on 2.1, it actually worked great. They didn't change any traffic. We moved them to 4.1, and their performance got so bad that like they are paging me every single day. And early tests show that this patch may bring back the performance of 2.1 for that workload. Now, granted, I'm trying to also get them to like stop doing that workload, which is a whole separate thing. But like until then. Cool. Any other questions? Sorry. Yeah, no. I like.
Have you measured TLAB occupancy?
Sorry.
Have you measured the thread level allocation buffer occupancy with this patch?
No,
To
not
see
yet.
if that causes any problems for how often it flushes?
Not yet. So those are the kind of things I want to test. Like ones, I think I'll have the confidence after Caleb's review and maybe David's test to start rolling this out in the small at Netflix. I should also say how it's turned on. So there's just a new Cassandra YAML setting that says how big is this buffer. If you don't set the size of the buffer, it doesn't turn it on. If you set the size of the buffer, it turns it on. Hence, you should have only set it to 256K if you're using EBS.
Okay.
Candidate for trust on it. Like it feels like a really good candidate. It's a long abstraction panel, and you use factors. You don't have to worry about stuff besides. This sounds like there's not really a strong case for cutting off.
I'm planning to turn it on by default once I gain that confidence. So yeah, I would make the case to turn it on in the community. It's just one hurdle at a time.
Okay, next topic.
Thank you all.
So happy to see so many great people. Thanks for staying for the latest talk with the It's 6 p.m. I'm going to stay out here for like 9 minutes. And bear with me here. All right, so first of all, a little bit about myself. My name is Bernardo. I'm newer to the community than most of the folks here. It's been really nice faces to a lot of people that have been talking to Slack So yeah, I've been working with Dinesh and James and some of the really interesting stuff with Cassandra. And yeah, we came up with this constraints framework that we presented and approved by the community. Thanks a lot to everyone who reviewed it and who provided feedback to the CP. It was a really nice and lively discussion. And let me go through it. So yeah, basically, first of all, what are we trying to solve here and why? So I like to see this and come back to one of the things that Josh mentioned in his presentation about large rows being a problem. That's really hard, and we hit that problem when working on the CDC CP that James just talked about. Because those large blobs are a problem on the transport side, but they are also a problem pretty much. There's not a great solution for that, and yeah, it's just a hard problem to tackle because Cassandra is flexible enough to allow anyone to do anything that they want, basically, and having some tools in the tool belt to try to reduce that overhead may be useful for operators or like basically data owners. So a couple of things here. First of all, we have a couple of guardrails already, trying to add those threshold limits to the size of collections or like, rows themselves. And I did propose a Jira trying to add more guardrails to that. That of course will add a little bit of overhead and configuration decisions to like take up front. Actually, Jordan was kind enough to provide this suggestion in which this is cool. We could turn this into like a generic or general constraints or cluster-wide constraints instead of having them as just guardrails. So yeah, that's current status, and here's where the constraints framework steps in. Basically, what we are proposing here is to have some definition on the table schema, defining what can be written on a row or for a particular table. And that can be defined in two different ways. One of them, as you can see here, just inline with a row or as a table level constraint. I'll go through what all of that means later on, but yeah, that's basically what we're proposing here. So what will happen here is that whenever we try to write a row, those constraints will be checked against what data we're trying to write. And if that constraint is not met, the write just fails. Yeah, so let me go through this. Yeah, I mean, there's a bunch of things that we need to be mindful of defining constraints. So as you can see here, there's two types of constraints here. This one is defining a separate function that will do something with whatever we pass here. And we'll have some parameters. I'll go through the exact constraints that we are proposing as part of the CP later on as well. So this is the actual syntax we are proposing. For the table level constraints, it's just adding a new constraint keyword that checks something. This is another new keyword. So this constraint name is something useful for whenever we want to alter those constraints or drop those constraints later on with alter table statements. As we can see here, for example, this is how you would drop a constraint for it not to be checked anymore. Now, this name is proposed to be as well optional, and if you're not giving it a name, it will just generate a random string. So you can, like, with a describe table statement, you can retrieve the constraints that are present and just alter them.
Okay, can you zoom in the video?
Yes. Is it better?
Yeah.
Very good. All right. All right. Now let's talk about errors. We're adding a couple of new errors to the constraint definition. One of them being, okay, the constraint is not met, so you cannot write here, or the constraint you're trying to define doesn't make any sense. Like, for example, we're trying to add a constraint with a length function, which is meant to be used with strings, but number of items is an integer.
that constraint wouldn't make any sense, so you cannot alternate it this way, you cannot add a constraint this way. And yeah, these are the proposed changes, as I mentioned before, adding the constraint keyword and the check keyword. Yeah, schema level. Okay, this is an interesting topic. We decided to go to just check the constraints when we are writing. Why is that? And there was some discussion on that. We decided to park it for future discussions because this brings a lot of interesting problem cases. Like, for example, what would happen if you start enforcing a constraint on already pre-existing data and there's finding data? What happens at read time? If you're enforcing constraints, do you happen that do you fail to read? Do you still return it, or what do you do? So that's the reason why we decided to just stick to write time and just call it a day. All right. So now, as for the initial constraints that we will be implementing, the PR is already out there. But yeah, basically, two types of what I like to think of core constraints. One of them being length, or loss or strings that will say that, okay, this is not longer than this amount, or integer, well, a number type of comparator that just can define a bunch of like relations here. So those, this is an interesting use case. Those can also be combined to be or to have creative use cases. Like, for example, this key space color, you're making sure that the RGB integers are just like, meaningful scales. So yeah, as I was mentioning before, for many types, we are proposing all of these constraints with max, min, equal, different. Similar thing for types like before and after with the equality. And then the length is the one that I was mentioning before as a core constraint, but then these other constraints will be proposed to the community as like separate discussions because they could be contentious. Like, for example, would it make sense to have an isJSON constraint or just create literally a JSON type? So those kind of things, I think that will bring up like interesting conversations, and we can have them one by one. The way we're proposing this is just having a couple of interfaces to implement new constraints. Yeah, which is basically this public interface that I'm mentioning here, with a couple of methods. Validate, that's the one that I was mentioning before, validating that when you're creating a schema, when you're creating a constraint, the constraint you defined is valid. And then executing it is like, okay, you're trying to write, this is the data you're trying to write, this is the constraint, just should I pass or should I fail? That's about it. And then one last item that I would like to touch on is interaction with guardrails. Because as I mentioned before, we already have some guardrails that define thresholds, which one should take preference. So the way we frame this is that I think guardrails is like more generic cluster-wide operation that can be set or defined by an operator in this case. And then the constraints could be left to the data owners. So for example, if a customer has, I'm always thinking about this, and I think John said multi-tenancy was bad. I agree, but it exists. And yeah, if we want to provide that flexibility, but still keep the protection for the rest of the cluster users, guardrails should be the way. And if you want to have your own business aware constraints, then you can use this framework. So that's how I'm framing it. And yeah, that's basically the CDP. Now again, as I mentioned before, we have I have a PR open already. If for anyone interested in just slamming me with comments, I'll be more than happy to address it. Yeah, at the end of the day, the code will be better, which is basically what we want. So yeah, that's basically that's the PR. So yeah, thanks everyone for.
So it seems like there might be some value in, like, if somebody expresses a constraint on the table, that means they expect the data in the table to be compliant with it. And obviously, you don't want to blow up on reads for existing data, but it could be valuable for people to be able to apply constraints to an existing table and effectively scan across it and say, find non-compliant rows. Is that something that you've thought about, or, I mean, it's slow as hell?
Yeah, it was something like that.
Yeah, but what would happen if you have constraints from you then?
So I think my concern with that, although I agree, is like we used to have this problem in first days where you wouldn't type a column and then you would type it after, and compaction would then verify the type. And at least when it was really bad, like it would just silently throw. I've lost it.
Let's not do that.
So my question would be if it finds things that violate the constraint in this process, whether even in repair or
Right. Well, I'm thinking like a note tool, yeah, just print out, hey, here's your clustering piece got.
Okay, so if it just printed them out, I'd be all for it.
Something like that, just to be able to say, okay, is there anything that I need to know about that I don't know? It's down to a way to express what bounds or reasons.
So that we like a self-constraint that reads. So hard
Yeah,
enforcement of
yeah.
right and
No
self-constraint
tool
steps.
verify soft dash constraints.
Or a soft constraint on reads that would give a client. You pull back data that didn't match the constraint.
So I think there's value in not just printing it out, but also creating some observability. What percentage of your data is dominant in it, right? So we all have schemas where people have shared like 100 megs of data in a block out, trying to build a block store, etc. In the wrong way. You can still build a block store, but from an operator standpoint, if we can bring that visibility, that makes a lot of sense.
Like a virtual table where you can see
Yeah,
the things that have constraint violations.
I think the point of my anecdote was before we do anything destructive with that information.
No,
make
yeah.
sure it's not- that's yeah.
Apply this constraint and delete all of the data. That would be
So I don't remember this when I read through this initially. Did we ever add a mechanism to add the constraint, but only like soft do it? Because the thing that I just realized is if you set it and then all of a sudden it starts rejecting like a ton of writes, you probably would want a way to kind of like ease into the bath, where you're like, oh, okay, like this thing isn't like there's going to be major problems if we enable this. Did we add anything like that?
No, we didn't. But it's definitely like something worth exploring.
Yeah, maybe it's like a table level parameter, like enforce.
Constraint one off or with constraint hard or something.
Or just warn or reject.
Yeah.
And be that
But
simple,
to
right?
Nash's point, if we do that, there needs to be metrics, so that like, if I turn it on soft, I don't need to like go to the logs on every item to figure this out. I just go to like my dashboard.
Yeah, because I can see
you have two boards, right? Enforce and just monitor and enforce. Monitoring will give you an idea of how many offenders are out there. And if you can map them back to identities, like these are the user IDs and IP address again, you can do go and change up the application.
But I am so excited to retroactively apply this to some tables. But I'm actually excited for the request to start failing.
Yeah, we can make that happen.
So, with all the other talk about analytics today, how would things like the bulk writer work? Would it just not be enforced and we wouldn't check on
Not
this?
be enforced, yeah, as Dinesh was mentioning, analytics just ignores all of this.
But analytics could generate things that were outside policy unless you added it in the S table.
Well,
Depends on where in the stack you put those checks. right?
Yeah,
exactly, yeah, we could just export that as part of
If
the
only
analytics.
Cassandra had an interface where you could just right and enforce constraints on the data, then that would.
I mean, I suppose that's part of the question. Are you thinking about implementing this as part of the S table writer implementation or as part of the query part?
You would have to do it earlier before we get something.
Yeah, you want to do this coordinator.
Yeah, so in that way, then other things could be generated.
But if it loads schema, and this is in a new system schema table,
If you trust within maybe S table, you
that's an issue.
yeah, but that's, you know, where's the boundary of trust?
Right, how does it work for closing and non-closing coverage? So I can understand.
So that's a question for whenever we talk about that constraint.
I mean, that's syntax, isn't it? Like, isn't it? It's just an in-called number of items.
Yeah. I think the name of the column
It's
makes you
probably,
think.
random name that it keeps, because it's an integer. But yeah, for crossing collections, stuff like that, that's a discussion that we will need to have whenever we decide on working on a constraint for those. Like the ones that I'm implementing initially to have something to build on top of. And I think that will unlock a bunch of conversations that we've been having just right now, are the length for string and blocks, which I think it's super useful, as Jason, Jordan was mentioning. And yeah, just for integers and vectors, which are also the simplest ones.
I feel like we have a number of users who are familiar with Postgres and think, oh, this constraint feature looks like Postgres and acts like Postgres. And if they can get reads that violate their constraints, I think it would be confusing for them. So I feel like the frozen discussion is something for them to, if we don't reject constraints on collection size for non-frozen, then that will be them going down a documentation rabbit hole of like, how
Frozen versus not frozen really doesn't.
right, I'm saying, but to ignore it, to accept the constraint and ignore it.
But I think the nuance here is Bernardo hasn't actually proposed any constraints on.
Oh, yeah.
I like what you see. I mean, this is exactly what I'm hoping for the future of
Yeah.
this feature. Actually.
Is that each
You know,
constraint can be individually.
exactly, yeah.
Sorry, I get thumbs up.
Oh, no. I'm super happy. I'm super happy too. So that's all I got.
Okay, I have an announcement to make before we wrap up. Steve Mazak from Amazon Key Spaces is offering a happy hour to Cassandra community members today. Tarantula Billiards from 6:30 to 9:30 p.m. So in order to join, you need to be subscribed as of now to the Cassandra dev or user list. So when you get there to Tarantula Billiards, which is nearby, just mention that you're joining Cassandra. Thank you, everyone.